We are given three vectors OA, OB, OC, and asked to find the cosine of angle ABC. Well, for me, a good idea, I'm just going to copy the question across, is to get a little diagram down of what is going on. So if I put the origin in, first of all, and take it up to A, then I have this vector, which is going to be -3, 1, -9. Another vector over here, B, 1, there's no J component, then -1. And over here, remember, this is in three-dimensional space. We don't really know what it looks like. I'm not, it's just a sketch. 5, 2, -5. And ABC, I can connect them. I'm interested in this angle here, which I'll call theta. And then I need this vector and this vector, because that's how the dot product works. For the dot product, you have your two vectors coming out like this, and here's your angle. So that means I need to find out what BA is. And to find BA, actually, let me just temporarily, I'll call this one little a, this one little b, and this one little c. So then to get from b to a, we can go minus b plus a, or equivalently a minus b. And that will be -4, 1, -8. BC is the other one. That will be c minus b, 4, 2, -4. And if we dot product them, then remember there's two forms of the dot product. We first of all can times the components, corresponding components. So I'll get -16 plus 2 plus 32, which is equal to 16 plus 2, 18. And I get the equivalent form, the magnitude of BA times the magnitude of BC times cos theta. So this, I can use 3D Pythagoras. It's going to be -4 squared plus 1 squared plus -8 squared, all square rooted, which is √81, which is 9. Similarly over here, 4 squared plus 2 squared plus -4 squared, all square rooted, which is √36, which is 6. Therefore, 9 times 6 times cos theta equals 18. I can actually cancel that 9 with this to give 2. So cos theta will equal 2 over 6, or 1/3. In this next part, we're told that the line L is an angle bisector of angle ABC. We have to show that an equation is given by this. We have a diagram, but I think a new diagram is a good idea here to really get at what is going on. Because typically when you're just given vectors, it's not it's not too bad to find the equation through 2 points, for example, but the angle bisector here is what makes it tricky. So I'm going to put in B here, and then I'll make it go horizontally along to A, and up here to get to C. And what we're interested in is it going exactly, that doesn't quite look half, does it? Exactly halfway. So this is a half theta, and this is a half theta. Now, unfortunately, what we can't do is like connect it up like this and find this point here, because at the moment we've got a parallelogram. If you draw a parallelogram and you bisect the angle, so, oh, sorry, if you draw from one end to the other, they won't be the same. Look, you can see that this is going to be less than this. So let's just think back. And actually, this is the crucial bit of the question. We know that BA is 9 in length and BC is 6 in length. So that means there will be a point, say here, which I'll call D, which will also be 6 in length. And what we have done absolutely crucially is constructed a rhombus, because now if I go the same direction here, here, this will work out. So I'm trying to say that I'll call this X. Essentially, BC will equal dx, and BD will equal CX. Actually, they're all equal. BDXC is a rhombus. So you have to realize to do that. You can't just be using A going to X, because then you'll have a parallelogram and it won't work, because if you go from here to here, it won't bisect. Whereas for a rhombus, it does. So we're on our way now, well on our way, because I can just bring the origin in. Now remember, I'm trying to find the equation of this red line here, line L. And so the standard approach is to get onto the line from O to B in this case. That's going to be a good starting point because we know that vector. In fact, we had it up here. O to B was 1, 0, minus 1. And then we just need to find the direction vector bx. So we have this bit here. That's going to be our 1, 0, minus 1. And we need to show that this is the direction vector. Right, we can do this because bx is going to equal it's going to equal bx is going to equal bd, not ba but bd, plus dx. But dx, sorry, I made a bit of a mistake earlier. I've just realized they're not all the same. The lengths are all the same, but bc is equal to dx and bd is equal to cx. They're not actually all the same because they're going in different directions, but they're all have length 6. Apologies if I confused you with that. Now we want to relate it to things we know, because I've just kind of sprung this point D out of nowhere. But what we can see is that it's a fraction of the amount of BA. And it's actually 6 over 9 of BA, or equivalently 2/3. So it's 2/3 times BA. And then dx is fine because that is exactly the same as BC. Oh, that's the hard bit, I think. Because once we've got that, we're back to just being able to calculate these things. So BA, we already had that. I can't remember where it's gone, but here it is. Minus 4, 1, minus 8. and BC, 4, 2, minus 4. This is looking a little bit awkward. So what I'm actually going to do is I'm just going to factorize a third out, keep the third out, and then I'll times through by the 2. So I'll get minus 8, 2, minus 16. And then if I factorize a third out of this one, I just need to times through by 3, 12, 6, minus 12. And so overall, I'm going to get a third. And then I can actually just add these. So I'll get minus 4, 8, and minus 28. And actually, there's a common factor of 4 here, so I can even factorize out. Let's just check the answer and just, so we wanted 1, 2, and minus 7. So in fact, that should have been 4 because it was minus 8 plus 12. So now I'm going to get 1. If I factorize out the 4, 2, and minus 7. 1, 2, minus 7 is a direction vector. I can ignore the 4 over 3. And equation of L, R equals OB to get onto the line, plus T times some amount of BX. Which is equal to that 1, 0, minus 1. I kind of just want to stick with it in column form, plus T now. Oh, they've already used T. Okay, I'm going to change this to lambda because technically I'm changing the constant T times 1, 2, minus 7. We've done it. So I'm just going to summarize that because that was not particularly nice. I drew a diagram. I think that's crucial. BCA. I drew the angular bisector in, and I identified that actually I cannot just connect it up into a parallelogram because that just doesn't happen from one end to the other end. Instead, I need to construct a rhombus. So I constructed D such that I would get a rhombus. This length is 6, and that means I can go along BC the same amount, equivalent, they're equivalent, and along CX, which is equivalent to BD, to create this rhombus that would necessarily, if I go from B to X, bisect the angle. That was the crucial bit. Like I said, I starred it because then I can write BD plus DX, but that's going to be 2/3 of BA plus BC. And then I put it through. I just had to be careful with that fraction. I mean, I could have multiplied it through and put it all over a common denominator. I would have ended up having to take it out eventually anyway. We didn't need to necessarily use D. We could have used a point up here and made it 9. And actually, when I looked through the mark scheme, that would have made it slightly nicer because it would have been BA plus 3 over 2 B, whatever this is here. And these do actually divide through by 2. So I went with like the more complicated route. And doing it that way would have been better. Like as long as as long as you're careful and you make sure you get a rhombus, you'll be okay. It's just you might make it as complicated as I did, or it might be a little bit simpler. But once we've got that, we've got the direction vector. Remember, we go from O to B to get onto the line, and I'm going to go some amount along this direction vector. That's our standard, concept for the equation of a line using vector form. and hence we get this, which is what was required. Amazingly, part C is actually like really nice, because we've already calculated, where did we do it? We've calculated that BA is 9 and BC is 6. So AB is equal to 9 from before. Now, previously we didn't calculate AC, so we're going to need to do that. AC is going to be C minus A. Remember, you basically take the second one and subtract the first one. I haven't actually drawn a diagram here. AC, I can go A to C, I can go minus A plus C, which is the same as C minus A. And remember, I called this C, didn't I? And this was A. So I'm going to get 5 minus minus 3, 2 minus 1, and minus 5 minus minus 9. And then we use Pythagoras. It's exactly the same as what we did for AB. We're going to again get 9. So therefore, AB, the magnitude is equal to the magnitude of AC. That one's not too bad. However, what part C really is doing is helping us out with parts D and E, which are back to complex, let's say. The first thing I think to do is like use that information. I'm going to now draw in what we have, this triangle, and I've on purpose drawn it as an isosceles triangle because we've just shown that two lengths are equal, AB and AC. So I'll put A up here, and then we know that we have a circle where they're all tangents. Now is that going to work? It's not great, is it? Okay, that's not too bad. So a circle S lies inside triangle ABC, and each side of the triangle is a tangent to S. I've set that up. Find the position vector of the center of S. Okay. Now let's think back to what we've already done. We found the equation of the line L. That, remember, it was the bisector of ABC. Bisector of ABC. Now, if I just connect up here to here, what I've created is a kite. I mean, you can use congruent triangles to prove this. But if you draw this line in, this length is the same as this length. This is the same as this. Like, the congruent triangles, this angle will be the same as this angle. And actually, this will be the bisector. Maybe I said that, but this is the bisector, and it will necessarily go through S. So this here is line L. And of course, that is an absolutely vital piece of information. Because now what we need to do is find the equation of another bisector, because that will also go through S. And I think using this one makes the most sense here. So I'll call this L2. Remember, we've got an origin over, say, here. And so now what I want to do is get onto the line, which we can do at A. And then we can bisect BAC. So angle bisector. I'm trying to set up why I'm doing this. We're going to basically have to find the equation of the line and then solve them to find this vector here, S, the position vector. Angle bisector of angle BAC. Well, what we can actually do now is similar to what I did before. You can imagine going along AC again. And this way is AB, and again creating a rhombus. So this will have length 9 and 9. And in this case, the direction vector will simply be AB plus whatever this is, but this is the same as AC, so it's going to be AB plus AC. And that is equal to 4 minus 1, 8. I think we calculated these earlier, didn't we? It's going to be the opposite of this. And then AC. Did we calculate AC? Here, 814. Which gives 12, 0, 12. Or 12 times 1, 0, 1. So equation of L2 will be R equals, we want to get onto the line, so we're going to use this vector OA, which is minus 3, 1, minus 9. And then we're going to go along some amount. We've used T before, so I'll use S times 1, 0, 1. Back to what I was saying, we now have the equation L2. We had the equation L before. The center of the circle is going to be where they intersect. Even at this point, you're thinking, for what is going on? I hope you can kind of see just the power of vectors. We're working in three-dimensional space, using geometrical arguments. And sometimes people say to me, like, why do we have all these different ways of writing down equations of lines? This vector form is just really useful. And, it's, yes, you can write them in Cartesian form as well, but they're just not as easy to deal with as in vector form. So where they intersect, I can set the x coordinates equal to one another. So minus 3 plus s equals 1 plus t. And then 1, the y components, is equal to 2t. That's brilliant because that immediately tells us that t is equal to a half. And then the third one, minus 9 plus s equals minus 1 minus 7t. So I'll call this one 1 and this one 3. So minus 3 plus s will actually equal 3 over 2. And s will equal 3 over 2 minus plus 3 rather. That's going to be 9 over 2. And I just want to check it. Like, this will help me see if I made a mistake. Sometimes you can show that things don't intersect, remember, by showing that the third one is not consistent. At this point, you might be running out of time, to be fair, but if you have enough time, let's just check. So the left-hand side will equal minus 9 over 2. So it's minus 18 over 2 plus 9 over 2. And the right-hand side will equal minus 2 over 2 minus 7 over 2. Okay, so this works. Consistent. Therefore, center has position vector. We can use either T or S back into one of these. So why don't I go with this one? So it's going to be 3 over 2, 1 minus 9 over 2. All right. This leads us to the very last part. We're asked to find the radius of S. So I might draw another new diagram. In fact, no, I won't. This is decent. I get rid of the rhombus aspect of it. So we have all of these position vectors, remember? The origin is, I don't know, it's over here somewhere, but we know what OB, OA, OC, and now OS are. And we're interested in finding the radius. Now remember, I didn't add it, but this was 6. So because of the symmetry of the problem, it kind of makes sense to look here, because this length will be 3 and this length will be 3. So I'm going to call this point X. And that full length was 6, remember? And then I can connect it up, X to S. This is the distance that I want to find. Okay. And what we have is a right angled triangle. Because this is going, because I've got an isosceles triangle, this must be a right angle. So I connect it here. And if I can work out what B to S is, I think I just realized that I think S was actually the circle. So I'm going to change S is the circle. I'm going to label the point. I can't call it C for center, so I'll call it N. And this length is R, and that's what I want to find. So we want to be able to find BN. And BN, don't forget, we've got this vector here as well. And we also have this vector. So BN is going to be minus this little b, because I'm going the opposite way, plus that vector from before, the center. I'll call it little n's not good because that sometimes means a normal vector. So I'll just stick with ON. So I'm just trying to, let me just explain that again. I've drawn another diagram. I've drawn the circle, and then I'm trying to find the radius. So it makes sense because of the symmetry of the problem to go from the center point between B and C, which I've labeled X, up to the center of the circle N. I know that BX is then 3 because it's just a half of BC. And if I go up, well, this is going this way, this is going this way. It must be for this isosceles triangle. Of course, it's somewhere in three-dimensional space. I don't know the exact orientation, but it doesn't matter. It's an isosceles triangle. It must be that this is a right angle. So if I can find the length Bn, I can use Pythagoras' theorem to work out nx, which is what I want. And I can find Bn because I know what OB is and I know what ON is. OB we had at the start of the question. ON I figured out a minute ago. That was the position vector for the center of the circle. So minus B, it's a lot easier when I do this on paper because I've lost track of where everything is. But minus B will be minus 1, 0, 1. Plus what we had a minute ago, 3 over 2, 1, and minus 9 over 2. Which gives a half, 1, and minus 7 over 2. So Bn, I can use Pythagoras, it's going to be a quarter plus 1 squared, which is 1, which I'm going to write as 4 over 4, plus 7 squared, 49 over 4, all square rooted. It will be 54 over 4. I might leave it like that for the moment. Therefore, radius, hey, we're nearly there, people, is going to equal xn, the vector magnitude of, and it's going to be 54 over 4 when I square my hypotenuse, minus 9 when I square my 3. Hey, here we go. Let's write it a common denominator, so it's going to be 36 over 4, which is going to give me root 18 over 4. Or I can write that as root 9 over 2. That's probably, as simplified as I can get, really. And we have completed this question.